present our assignment number 1, which is about powder metallurgy and additive manufacturing. Our presentation line out will start from introduction up until conclusion. According to German, additive manufacturing and powder metallurgy are essential technology in modern engineering, enabling the production of lightweight, high-strength, and complex components used in aerospace and advanced industries. Powder metallurgy supports efficient high production through precise powder processing, while additive manufacturing, especially laser powder bed fusion, offers unparalleled geometric freedom for creating internal channels and optimized structures. Powder characteristics produced through automation, milling, and oxide reduction significantly influence flowability, packing density, and final material properties. Additive manufacturing quality depends heavily on controlling energy input, scan strategies, and post-processing to minimize defects such as porosity, cracking, and distortion. Material selection. Additive manufacturing, specifically laser powder bed fusion, is the most suitable choice for titanium, aluminum, and vanadium turbine blades. The design requires internal cooling channels and complex aerodynamics geometry, and conventional powder cannot achieve efficiently. Additive manufacturing eliminates tooling, reduce lead time, and support rapid design iteration for aerospace application. I'll hand over to Mr. Van.
Advantages of additive manufacturing. Design simplicity. It allows the creation of conformal internal cooling channels impossible with PM. Supports the lattice structure through optimization and thin wall geometry. No tool mold or die required. Significantly lower the iteration cost. The mechanical properties. The additive manufacturing TI6AL4V achieves near wrongly strength after HIP. Okay. Sorry about that. After HIP and heat treatment, the mechanical properties depend on minimizing porosity and residual stresses. Surface finishing improves fatigue, live aerospace applications. Production cost. The additive manufacturing cost effective for low volume aerospace component required engineering flexibility, including 2019. Also, PM has lower cost at very high volumes, but struggles with complex geometries. The additive manufacturing assembly steps because internal features can be printed directly. Next slide. The flow diagram. This flow diagram illustrates the process flow for additive manufacturing using the layer power bed flow fusion, which involves two parallel streams, one being raw material and the other one being the additive manufacturing build processes. The raw material stream focuses on powder management, including the storage, steaming, and control and quality control, while the additive manufacturing process stream outlines the steps involving in creating parts from powder inspection to final testing and certification. The two streams converge at the variable point, one output being high qualified outbound testing and certification procedures. The process involves the multiple stages, including powder storage and the regening, pad removal and powder recovery, heat treatment and mechanical testing, including production of high quality pads with complete and structure. Slide.
Thank you. These are the following are possible additive manufacturing defects and solutions. Porosity from lack of fusion or gas entrapment can be solved by optimized volumetric energy density and HIP. Residual stresses leading to wrapping can be reduced through preheating and stress relief. Fatigue issues from rough surface can be mitigated through machining and polishing. These are the recommendations for additive manufacturing process parameters. Layer thickness can range between 20 to 40 nanomicron for high precision. Laser power can range between 200 to 400 watts. Scan speed can range between 800 to 1200 millimeters per second. Inert atmosphere can be less than 100 ppm to avoid contamination. For post-processing, HIP to remove internal porosity and enhance fatigue performance, heat treatment, solution plus aging to reach aero-grade strength, surface finishing of critical areas such as leading or trailing edges. The overview of powder metallurgy production methods. Powder metallurgy performance depends strongly on powder characteristics such as particle shape, size distribution, flowability, and sintering behavior, all of which are influenced by the powder production method. Atomization produces metal powders by breaking molten metal into droplets using high pressure gas, water, or air jets. Gas atomization generates spherical, uniform powders ideal for high performance parts like aerospace components due to better flow and packing. Water atomization forms irregular, angular particles which reduce flowability but improve green strength after compaction because of increased surface roughness. Method will take over.
Okay, so I'll be taking you through the continuation of powder metallurgy production methods. Two being milling, mechanical milling, which uses high energy ball mills to repeatedly weld and fracture metal particles, forming angular or flaky powders depending on milling conditions. This method increases surface area and broader size distribution, enhancing sintering kinetics, but also increasing the risk of contamination from the milling media. Three being the reduction of metal oxides, which converts metal oxides into metal powders using reducing gases such as hydrogen and carbon monoxide. The process produces spongy, porous powders with fine particle sizes and high surface area, enabling an excellent sintering behavior from structural PM compounds. Next slide, please. And then this is our processing steps in powder metallurgy. Firstly being powder production with either element or alloy metal powder. And then we go to blending of powders with lubricants or alloying additions. And then we have compacting into desired shape using mechanical or either hydraulic presses. And then we go to sintering at high temperatures to bond particles without melting them. And then we have secondary operations, which include sizing, and then it goes to heat treatment, infiltration, and then it goes to machining to achieve the final tolerance and the desired mechanical properties. And then we have our final product. Thank you. I'll hand over to the next speaker.
Thank you. I will start with common defects that occur in additive manufacturing and how they affect the final part. So our first defect is porosity, which happens when the powder does not pack properly or when the gas gets trapped during melting. It can also be caused by poor fusion between layers. So these small forces act as a stress point, whereby they reduce the fatigue life and make the part weaker under the repeated load. So our second defect is cracking, which is caused by very high thermal gradients during the melting and cooling process. So the rapidity and cooling create internal stresses that the material cannot handle. Cracks reduces ductility and can lead to early failure of the component. So our third defect is distortion, which occurs because of uneven heating and cooling during a layer by layer building process. This causes the part to bend. Distortion affects dimensional accuracy and can lead to problems during assembly. So these defects show how important process control is when working with additive manufacturing. Can you go to the next slide, please? So for quality control, we use non-destructive testing, which is NDT. The best method we choose for additive manufacturing part is X-ray computed tomography, which is also called CT scanning. So CT scanning allows us to see the inside of the part in 3D without touching it. It can also detect pores, cracks, or fusion and other internal defects. CT gives accurate results and keeps the part intact and ensures the final component is the safety and performance required. Next slide. So in conclusion, both processes, additive manufacturing and powder metallurgy, play a crucial role in modern engineering. Our additive manufacturing offers excellent design freedom and also allow us to produce complex chips that traditional processes cannot. So powder metallurgy is still efficient for high volume production. And so for additive manufacturing, understanding the powder behavior, the process parameters and defect mechanism is very important to achieve high quality components. So by using the right tools like CT scanning helps us to ensure the parts meet the strict and additive manufacturing continues to improve manufacturing by giving engineers more flexibility, better design, and strong performance for advanced application. So our next slide is references which we use during our assignment. So thank you. Ya, was to para gudi, sarang ko.
Next abon ro gusto pa kay. Bili kay.